Hello guys, welcome back to Maison African Motives, still on our industrial electronics and for working on the transistors and amplifiers. In this case, we shall be focusing on the H parameters for dynamic values dealing or working for dynamic values. What is it that you're gonna need on our H parameters? I've got questions that you're gonna consider. I want us to start from the basics here. I think this one, we've got a diagram that you can just consider. This is from our industrial electronics and for textbook, whereby we are given, in this case, the information, use the characteristics. So we're given here curves. So we've got the two curves that we are given in Fig 5.36 for the common emitter. So we're talking about a common emitter amplifier to calculate by means of approximate method. So that is approximate method. The following, we've got the input impedance. HI represents input impedance, all right? Then E is for the common emitter. And this one is the reverse voltage gain, all right? But for the common emitter, the forward current gain for the common emitter. Then we've got 1 over HO is the E output impedance, all right? But the HO on its own like this represent what we call the conductance. So that one is conductance, which is measured in Siemens, all right? We shall talk about that. So what happens is that when you are given this condition for dynamic value, I want you to understand, when you are working with dynamic values, all you need is to know which formula to use for each gain or impedance or whatever that you talk about. Is it reverse voltage gain or so forth? All right. So we are going to consider here that it's a common what? It's a common emitter. Remember, on our common emitter, this one, it's an advantage because they gave us the characteristic curve, which shows us the input. The input, this is what we have. We are going to talk about the input current being the base current. So we're going to talk about the change in base current from the minimum, which is 10, to the maximum of 30. So we're going to have that is this one minus this one, that is the change in current. Then we also have the change in base emitter voltage in this case, whereby the maximum voltage it is 0.69, the minimum voltage it is 0.67. So here, this value here corresponds to 0.67. 0.68 is for the middle part here for this 20. That's the 0.68. Is just that the way they typed there, it was not corresponding. All right. So this is for the input. Then for the output, we talk about the voltage between the collector emitter, the output current being the collector current. That's for a common what emitter. All right. Remember this diagram, guys. We talked about this from our N3. The diagram of a common emitter amplifier, it's like this. I'm just gonna have a sketch. All right, so at the input, we're just gonna have a capacitor here. Then we've got our voltage divider from the two resistors. All right, let's just, this one is too big. I'm just gonna have this as a sketch, guys, for our common what? Common emitter amplifier, so that we understand each other. What is it that is happening on these H parameters? Because if we do not have this, we are going to have a lot of confusion to say what is it that is happening, of which you just need to know your voltages, because the voltages that you use for a common emitter are not the one that you're going to use for a common base. We are going to work with the two, common base and common emitter. All right, so this is our input. We've got V in. The capacitor here, we've got the resistor 1, and we also have resistor 2. This is our transistor, and we're gonna have a resistor for the collector there. All right, let's just have something of this nature. Then this goes to the output. We've got I'm not gonna focus on this much. I just want you to understand on the voltages and currents. All right, so at the input, the voltage that you're going to consider is between the base. Remember, this is our base, this is our collector, this is our emitter. So this is the voltage that you are going to consider at the input. We are going to consider VBE in this case, all right? So at the input for a common emitter, we are going to consider VBE, all right? At the output, this is our output here, whereby we shall talk about V out. We shall talk about the voltage that is between the emitter and the collector. In this case, we can just write as VCE, all right? Or it was EC, but we can just write as what? VCE. So at the output, you shall consider your V out in this case as your VCE or VEC, all right? That's the condition. So this is the input, all right? This is the input. This is the what? The output. On a common, sorry, hey, all right, sorry, guys, here, see what I'm writing here? This is the input, all right? This is the output voltage. Talking about the input current, the current that is going to enter here is the current affecting the base. So the input current, we are talking about the current at the base, all right? For the output current, in this case, the current that is going to pass here is the current for the collector. We are talking about the collector at the output. So our current out is going to be the collector current. That's for a what? For a common emitter. It's different from a common base. If I talk about a common base, we shall see that it will be different. The other things will be different. We shall talk about that. But here I want to focus on the common emitter. So meaning to say, the moment we talk about the change in voltage in, this will be the change of VBE. The change of V out, it will be the change of VCE. The change of current in, it will be the change of IB. The change of I out, it will be the change of IC. That's it. If you just understand this concept, then you are done. Input and output for a common emitter amplifier. So the question is, we are asked to calculate these parameters, in this case, from our information, we are asked to calculate. So I think we saw our information and our diagram. So I'm just gonna, okay, remove the diagram later on. So this is what you're gonna do. Let me explain here. We are given, calculate the input impedance, as we know that HI is for input impedance, E is for the common what? For the common emitter. So we are going to need the first question. All right, let's just have this. That is the first question, just gonna write as A. All right. So we are asked to calculate the input impedance. So the input impedance is HI, which is the input. But because it's a common emitter, we're gonna have this E. So in actual sense, the input, this is impedance, guys. We've got input, we've got output. How do you calculate input impedance? You are going to talk about the voltage at the input, the current at the input. So the actual formula was supposed to be the voltage at the input over the current at the input. But here we shall talk about the change in voltage. So it's going to be the change in voltage at the input, the change in voltage, the change in current at the input. This is at the output. If it is at the input, if it is at the output, we're talking about output impedance, which is 1 over HO in this case. We shall be talking about the voltage there at the output and the current there at the output, which is the change in voltage, change in current. That's the idea. Because it's impedance, guys. Impedance does not change. Voltage over current, that's what we know about impedance from our industrial electronics N2. Does not change. So the question is, we are talking about a common what? A common emitter, whereby at the input, we are given VBE and IB for current. This is what I was explaining here. At the input, in terms of voltage, we shall be talking about what? VBE. At the input, in terms of current, we shall be talking about IB. This is exactly what they are giving. So this characteristic curve can help you if it is like that. But under exam condition, mostly they don't draw this. They just give you values. You are supposed to know what to use. All right, so let us conclude our formula. So like I said, the change in V in simply indicates the change in what? In VBE. So it's gonna be the change in VBE at the input, then the input current, which is the base current. And this is exactly what we have here, the change in VBE, the change in base current at the input. All right, so let us substitute our values. So that's it, we're gonna have our input impedance. So the change in base emitter voltage, that is it's maximum, it's just maximum, or a change in this, maybe it's change in temperature, change in voltage, change in current. It's always a maximum minus minimum value concept. So that's it. Maximum value 0.69. That's 0.69 minus the input, which is 0.67. So the units there is just volts. We are not given millivolts or microvolts, just direct, all right? Then the current at the base is going to be maximum minus minimum, but take note of the units of current. Our current is measured in microamps. So it's measured in microamps, which is times 10 to the exponent of -6. So meaning to say it's going to be 30 minus 10 in microamps. So maximum current here on this sinusoidal function, the maximum was taken from what? 30, minimum 10. So that's 30 minus 10 for the change in the base current, which is at the input. So that's 30 minus 10 in microamps. Take note in microamps. So it's going to be 30 minus 10 in microamps times 10 to the exponent of -6. So that was going to give us the input impedance in this case. So, all right, let us just see on our calculator, what are we going to have for this input impedance. All right, so that is going to be 0.69 minus 0.67 over, just open a bracket, that's 30 minus 10 like this, close the bracket, times 10 to the exponent of -6. So that's a 1000 ohms in this case. Remember, this is input impedance. So that's 1000 ohms, which is approximately, or you can just write as 1 kilo ohm. So that is what we are going to have at the input impedance of what? Of a common emitter amplifier. All right. So that was our input impedance. All right. So we've got input impedance, voltage over current, but at the input. All right. Then we have got the reverse voltage gain. All right. Take note when they say reverse voltage. Remember, voltage gain, the normal formula for voltage gain is supposed to be voltage V out over V in. That is the normal formula. But if they say reverse voltage, we are going to interchange this. So it will be VI over V in. So it is VI over V out. That is voltage gain when reverse. So reverse, we just interchange our formula, right? Our normal formula, we know that it's out over in. But now it's reverse, so it's going to be in over out. That's it. So that's the condition there. So meaning to say, we are going to consider the output, and at the same time, we are going to consider the input in this case. All right. So let me just remove my diagram here, guys. I talked about this. I hope we have this diagram in mind and just understand. You can also as well use your textbook so that we catch up together. All right. So that's the B part. We are going to consider the reverse gain. Like I said, when it is reverse, you have to interchange because it's now reverse. We're going to interchange. So it's going to be V in over V out. So our reverse gain for the common emitter in this case is going to be the change in V in over the change in V out. It was supposed to be V out over V in on a normal sense, but because it's reverse, you interchange. But remember, at the input characteristics, the input voltage is VBE, which is the one that we indicated. Remember, input is VBE. So we are going to have the change in VBE over at the output voltage is VCE, which is the one that you are given here. At the output, the voltage there, it's what? It's VCE. So we're going to talk about the change in VCE. So that's it. We've got our reverse voltage gain in this case. All right, so the change in VBE, we talk about the input VBE, it's from 0.67 to 0.69. So it's 0.69 minus 0.67 over the change in VCE at the output. At the output, it's from 5 to 15. This is where it is affected. So this is output, this is input, which is 5. So that will be 15 minus 5 in this case. All right, so we've got 15 minus 5, and the units there is just voltage. We are not given like micro or millivolts, so there's nothing special there. So you guys and your calculator, use your calculator properly, you're going to obtain 2 times 10 to the exponent of -3. This as a decimal is same as 0,002. If you want to write it as a decimal, it will be 0,002. All right, so there it's a gain. There is no units there because remember, we are dividing the units of what? The voltage over voltage in this case. So there's no unit for this one. But here we've got units, it's impedance, guys, impedance measured in ohms. All right, so that is how we ended up with this reverse voltage gain. Then we talk about C, which is the forward current gain. So this is the normal gain that we know. So the gain for current will be V out, I out over I in. All right, I out over I in. This is forward. It's the normal one that we are used to. So that is, we are going to consider output over the input. All right, that will be our gain. So let us just have it here. So the gain, in this case, in terms of our H parameters, it's given as HF. HF is for forward current gain, but the E it's for common what? Common emitter. So we saw that this is forward, it's the normal current gain that we are used to, which is going to be output current over the input current. So remember what I say, the output current at the characteristic curve here, this is the output. It's given as IC. So this is what we have here. What I talked about, I think I talked about here. Output current, it's IC. So just one and the same thing. So you can just use your characteristic curve, or you can go back to the normal formula. Then at the input, for a common emitter, the input current is referred to as the base current, which is IB. So we're going to have the change in IB, which is the change in what? In base current. So that's it. We're going to have our forward current gain. So IC, which is the collector current, was taken from where? From the units also are very, very important. IC here is given in milliamps. These are milliamps. So it is taken from 1, this is the minimum value, to the maximum value, which is 3. But in milliamps, it's going to be 3 minus 1, maximum minus minimum. All right, so that's 3 minus 1. 3 minus 1 times 10 to the exponent of -3 in milliamps. Then IB, we talked about this before. Here, IB, the change in IB, which is 30 minus 10 from what we talked about, this 30 minus 10. But IB, take note, it's measured in microamps. So it's going to be times 10 to the exponent of -6. So it's 30 minus 10 times 10 to the exponent of -6. These are amps, these are amps. So meaning say they will cancel, and we do not have the unit for the forward current gain. All right, so if we are to simplify this properly, we're going to obtain 100 in this case. All right, so that was our forward current gain for the common emitter amplifier. Then we need, or at the end, we are going to need the output impedance, 1 over conductance. It's output impedance. All right, so you've got the input impedance. Remember, I said impedance is simply voltage over current, but this one is the output impedance. All right, so that is going to be the D part. So 1 over conductance, HO, it's for the output, which is conductance, gives us impedance in this case. All right, so impedance is 1 over this, but as we know that impedance at the output must be voltage at the output over the current at the output. So that means in terms of a common emitter, we shall just have E there for a common emitter. So it means our output impedance, which is 1 over HOE, is going to be the voltage. We're going to have the change in voltage over the change in, but remember, this is output voltage, output current. What do we have at the output? At the output, our voltage, it's VCE. Our current, it's IC. So it's going to be the change of VCE at the output, the change in VCE voltage at the output over the current at the output, which is IC. So we've got collector, emitter, then we've got the collector current. So that's 1 over conductance gives us output impedance. So this is the output impedance, guys, 1 over HOE, all right? So we're just gonna substitute the change in VCE, guys. I think we talked about this. Okay, I removed it, all right? I think I removed it, all right, no problem. Okay, change in VCE here, we talked about this, 15. Okay, let's just use, because we have it, output here. So it's 15 minus 5, all right? So that's 15 minus 5 there. So you're gonna have 15 minus 5 over the change in current at the output, and our output current is IC. From the output characteristics, IC is taken from 1 up to 3 in milliamps. So it's 3 minus 1 in milliamps. So you're gonna have 3 minus 1 in milliamps. That's times 10 to the exponent of -3. So that is going to give us the output impedance in this case, which is measured in ohms. Remember, impedance is measured in ohms, and that was going to be 5,000 ohms in this case, or simply 5 kilo ohms. All right, just use your calculator properly. That's what you're supposed to have at the end. So take note, which part are you working with? Are you working with a common base? Are you working with a common emitter? The answers are going to be different according to what you are working with. According to what you are working with. So this one, it was a common emitter amplifier. So that's why we have got VCE at the output, IC at the input, and VBE at the input, and IB at the input, like I showed you from that diagram of a common emitter. So we have got the same condition here, VBE and VCE, IC. So this one again is for a common collector, as we can see. So that's one and the same information. In fact, one and the same diagram, and this is just one and the same diagram. So as you can see, this one, you can just try to close up your work, redo this question as it is, all right? Just close your question where you are writing, then redo the question so that you see if we are together. So I'm gonna answer this one with you, since that other one was just a common, it was just a common question, like previous question as it is. All right, let's check this question is from April 2016, 15 marks on transistor and amplifiers, whereby we are given a common base. Yeah, that's good, so that we mix up with the common emitter that we talked about previously. So this time we've got a common base. It produces an output of, and we are not told. So take note, this time we are not told what this output represents. You are the one who is supposed to know the output of a common base amplifier. That one, you are supposed to know it. That's why I was saying you are supposed to know your diagrams, and from your N2, I think N2 we talked about this. So anyways, let's just maybe have our diagram here for a short revision. That's for a short revision. Remember, this time we are dealing with a common base in this case. All right, this is a common base. Why is it? Let me try to reduce maybe a little bit like this. All right, so we are dealing with a common base. So this is a common base amplifier. So just gonna have a sketch here. Remember, a common base amplifier, the base is the one that is at the common point. So maybe you're talking about an NPN transistor or what, but here I'm just gonna have a sketch. All right, so let's just say this is our emitter collector to the base. So, all right, then we could add the input here. So the input will be connected direct like this. And okay, just need a capacitor there, just maybe a capacitor at the input also, so that this will not cause a damage to our transistor here for the regulation purposes. All right. Right, we're gonna have here. All right, let's just have something. At the output, we're gonna have another resistor. Yes, we're gonna have another resistor here. Okay. And another capacitor at the output. I'm not worried about these capacitors, guys. This part of the question is not about this diagram. I just want you to just recall your currents and voltages. All right, so I'm just going to focus on the voltages and current. Yes, this is VC. This is our input, which is our VN. and we've got V out. All right, that's it. We have got our transistor. This is our base. This is our collector, and that's our emitter. All right, so the most important part that I want us to check is the input. All right, so what is the input in this case? What do we consider as the input voltage, the input current, and so forth? All right, so at the input, the voltage is still the same, VBE, just like the previous part. So our V in is gonna be considered as VBE. So if it is changed in V in, it will be changed in VBE, all right? Also at the input, we talk about the input current, which is the input current. There is going to be referred to as the emitter current. This is where we have the emitter, so that will be our emitter current in this case. So we shall be talking about emitter current at the input. So if it is the change in this input, it will be the change in emitter current. That one, I think we talked about it now, clear. All right, let's talk about the output in this case. At the output, in terms of the voltage, this is the voltage at the output, which is affected by the branch of the base and the collector, the base and the collector at the output. So meaning to say, V out, I'm just going to take this as the voltage of the base collector. All right, so if I talk about the change in V out, it will be change in of VBE. That's it. And the output there, we are talking about IC, the current that is going to flow here at the output, that will be IC. So the output current is going to be IC in this case, all right? So if I talk about the change in output current, I'm going to be talking about the change in the collector current. That's the idea. That's the whole idea. It's a common base, so you have to take information from a common base. So the question here was, let's check our question. We are given a common base amplifier produces an output of 6 milliamps. It produces an output of 6 milliamps with an input current of. So this product, which is the current, is at the output. And at the output, what do we have? At the output, we have got IC. So we are given the change in collector current at the output because it's a common base. So this time we are given the change in collector current at the output, which is 6 milliamps. All right. So at the output, we've got 6 milliamps. So this is for the output. All right. Taken from the input of what? 5 microamps, the input current being 5 microamps. So the input current, I said, is the emitter current. So you're given the change in emitter current, which is 5 microamps. That was 5 microamps. This is for the input. All right. Then also we are given the output voltage changes with it change. There's a change of, so these are just change in voltage, change in current. It changes by 8 volts at the output. So the change in V out, which is VBC at the output, you said VB. So you're still at the output here. So you're gonna talk about VBC, which is the change in the voltage, all right, which is the output, which is 8 volts. We are given as 8 volts. This is at the output. Still at the input, we are given the information at the input, whilst at the input by means of 4 volt input voltage. So we are given the input voltage. So the change of input from 0 to 4, it will be a 4. So that will be the change in this case of the voltage at the input, and at the input it's what? It's VBE. So that's VBE. We are given the value of VBE, which is 4 volts. So this is what you just need, because you are dealing with what? A common base amplifier. Know the characteristics there so that you know which voltage. Yes, we can just use changing V out over changing this. If you want to avoid now this VBE and this VC what. If you want to avoid that, you can just use these ones as they are. Changing V out, changing I out as they are. It's still you win. You can win if you want to avoid this, but know your values at the same time. All right, so the question was to calculate the following dynamic values. All right, the first one is the input impedance. All right, we talked about this from the last question. The input impedance, we said, is given by HI. All right, so I'm just going to take this information. So remember what we said, that's 4.11. So we said the input impedance, in this case, input impedance. All right, that's input in impedance is given by HI in this case, that's HI. But it's for what? For the common base. So we are just gonna use a B for the common base. So this is what you're asked to calculate, right? So the question is, how do you calculate the input impedance? The input impedance is not going to change. Always is the change in voltage at the input over the change in current, voltage over current, but at the input, because we're talking about input impedance. All right, but that change in voltage at the input, remember, V in, it's what? It's a VBE. So we are simply talking about the change in VBE over the change input current, which is the change in IE. So you can just substitute our values. VBE, that is, it's 4 volts over change in IE. The change in IE is 5 microamps. So that's 5 times 10 to the exponent of -6. So that was going to give us the input impedance. If you simplify properly, you're going to obtain 800,000 ohms, all right, which is simply 800 kilo ohms, all right? You can just write in short 800 kilo ohms, all right? So that's for the input impedance, voltage in over voltage out, but the voltage in is the base emitter, all right? The current in is the emitter current. That's the whole idea there, all right? So let's check the other part. Then here they need the output conductance. Remember the last question, it was output impedance, not conductance. And I said output impedance is taken from the output what? From the output conductance, where we said, because we know from the impedance that, all right, this HO like this, let me write it aside. This is 4.12. The HO is for the output conductance, not impedance. But the moment we write as 1 over HO, is now equivalent to impedance. And we say, as we know the formula for impedance, this is the one that we are used, voltage over current. So it must be voltage over current. But now we no longer need impedance. We need direct this conductance HO. So HO is 1 over Z. So if HO is 1 over Z, it means what? Because we are saying 1 over HO, it's a Z. So you can make HO the subject, which is going to be 1 is equal to ZO. HO, we divide by ZO. So HO is 1 over ZO, of which Z is voltage over. This is what we know. Impedance, guys, voltage over current. But the moment you say 1 over, you're going to interchange this. So it's going to be current over the voltage at the output. So that means whenever you are calculating the output conductance, you're going to use current over voltage at the output. But this is the output conductance of a what? Of a common base. Take note here. It's a common base. So you're going to have this as HOB like this for the common base. Is equal to the current for the common base at the output is what? The current for the common base at the output, it's IC. So it's going to be the change in IC. It was supposed to be like this. So it's going to be the change in IC, which is output, over the change in output voltage. Our output voltage for a common base, the output voltage is VBC. So we are going to use the change in VBC. That's it. So that's our conductance. So the change in collector current, remember we have these values, our change in output current, which is collector current. We have it on top here. Collector current, it was 6 milliamps. So these are milliamps. So it's going to be 6 milliamps. 6 times 10 to the exponent of -3 over the change in VBC, which is the voltage at the output. VBC is 4 volts. So we're going to divide by 4 volts in this case. So that's going to be 6 times 10. VBC, is it 4? VBC. VBC. So at the out, when I'm taking input, VBC, this one. VBC, sorry for that, which is 8. So that's 8 volts there. Remember, we're talking about VBC. So it will be 8 what? 8 volts. So that's it. We've got the conductance at the output. So if you were to simplify this, you're going to obtain 7,5 times 10 to the exponent of -4 in Siemens. All right. Conductance is measured in Siemens like this. All right. Then if it is impedance in ohms, all right, impedance, which is 1 over conductance, output impedance is 1 over conductance measured in what? In ohms. So if the question was, if you were asked to calculate the output impedance, you're going to write this as 1 over, the output impedance is 1 over HO, all right? So for the base, it is going to be for the base like this. So that will be the condition. For output impedance is 1 over like this, but this one, they need direct the conductance. So this is what they needed, all right? That's for the common base, and I talked about this given information. Then the other part, we are given the forward current gain, all right? The forward current gain. Remember, I said if it is forward, you use the normal formula. Reverse, you interchange. So the forward current gain is simply output current over input current, all right? So let us just have it here. You can just even try to put it here because we're done on this part. So let's just remove this one. All right, so like I said, when dealing with forward gain, you use the normal formula, output over input, but reverse is you interchange input over output, all right? So that's in this case 4.13. We need the forward current gain, forward current gain. So the forward current gain given by HF, that is the forward current gain, but it's forward for the common base. So you're gonna have a B for the common base. Remember, we had E for common emitter, it was HFE, but now gonna have B for the common base. So meaning to say, we can use this formula. Remember, I said if it is for a forward, use the normal formula as it is output current over input current. That's our gain. So we're gonna have the change in output over the change in input. But remember, the output current for a common base, if you're talking about a common base, the output current is the collector current. So you're gonna talk about the change in collector current over the input current, which is the emitter current at that moment. So we are going to use the emitter current at the input. So that's it. We are going to calculate our forward current gain. So let us just substitute our values. The change in collector current, which is the output current, our collector current is 6 milliamps. It changed by 6 milliamps. So that's 6 times 10 to the exponent of -3 over the change in emitter current, which is at the input emitter current. That's 5 times 10 to the exponent of -6, 5 microamps, 5 times 10 to the exponent of -6. So we are going to have the gain, and the gain does not have the units, all right, which is 1,200. Because we've got amps over amps, these two we will cancel, you obtain 1,200. So as you can see, those are the questions on the gain, all right? But we cannot just leave out the other questions. Let's just talk about these other questions, because here we are given, use the graph to illustrate by what is meant by crossover distortion and explain how it can be minimized. All right, remember, the crossover distortion can be actually presented in terms of a graph. Let me just try to show you something here. I think I've got a crossover something here. I want to show you from your textbook so that you can also understand what we are talking about. So this is what we have. I don't know if it is clear enough. So if we are given a complementary symmetry push-pull class AB, that's what we talk about. The crossover distortion is once again eliminated by bias. So this is the elimination part, but the actual part of crossover distortion, it occurs at a condition during the period when the transistor begins to switch off and the other starts to switch on. All right, we are given one switches off, another switches on. So this is the distortion that we are given here, the crossover distortion that we have here. All right, for the transistors, we have got the crossover distortion between this indication here, just like this. All right, this part here that we see here. All right, this part that we see. All right, so that is the idea that we're going to be talking about. We've got the collector current of Q1, the collector current of Q2, the second transistor for a second time. So one switches off, one switches on. So that is the idea that we are given there. And I think we have seen that in class B, amplifiers suffer from what is known as crossover distortion. Since in class B, the transistor is biased at cutoff, the input signal must first rise above 0.6 volts before the transistor starts to conduct. This condition is clearly shown on the waveform below, which is the one that I showed you. If the input signal varies, the circuit will not respond until it exceeds the forward bias voltage of the transistor. All right, so that's it. And the minimization part is this one that they are trying to talk about here. But in short, we can just say it can be minimized. So the graph that they needed is this one. I think I'm talking too much here. The graph that they needed is this part. So you can just take this piece here, the end, this one at the end, this one. You can just take this part as it is. It's fine to indicate a crossover distortion. All right. But here they are saying this same crossover, how it can be minimized. All right. So this can actually be minimized if the transistor is biased slightly above the cutoff value. So if the transistor, it can be minimized if the transistor in this case is biased. So if the transistor is biased in this case, all right, so we're talking about the transistor being biased slightly. All right, sorry for that. Let me just try and save. That is slightly above the cutoff. All right, slightly above the cutoff. All right, so we've got the cutoff value. That's it, slightly above that cutoff value. And 4.3, a field effect transistor is a voltage control device. True or false? Oh, that's a true, because we see that FET, which is a field effect transistor, it is actually a voltage driven or voltage controlled device where the output current is controlled by the input voltage. So that one is a completely true, right? That's true. And draw a block diagram of a negative feedback for marks. All right, negative feedback, we must have the input in the forward side. So that's 4.4. This is negative feedback. So you're going to have this into the summation point, then to the amplifier. So you're going to talk about the amplifier here. So these are amplifier like. All right, then this one is just direct. All right, but when it is got a feedback, it's now going to be considered back. All right, we now have a feedback. So we are going to consider this back to the summation point. So this is just a signal of the feedback. All right, this is our feedback signal back to the what? To the summation. So that's the idea there. So we've got the input, which is V in or VS, because this is our saturation point where we talk about summing up. All right, so that's our summation. That's our summation point, this one. All right, then we are talking about the amplifier. So we'll be talking about the amplifier. So you can just indicate with A to the output. So this is our V out. Then this beta, beta indicates the feedback network or signal. This is the feedback network. That's our diagram, simple like that. All right, so that's it. It's being compared there. It goes back to the summation point. That's with a what? Negative feedback. It will be given back here to the negative. All right, so guys, I don't know, there is any part of transistors that we need to work on, let me know so that we can just work on that part of the transistors. I think it can help us even to explain a certain topic from this textbook, maybe it's theory part. I think it's clear, but we can just even go back to the textbook and revise, such as what I'm trying to say. We can just use a PDF like this, and so that we can just explain some other things that are important, but as you can see, it's direct and straightforward to the point. Yeah, let us just revise as much as we can.